Okay, so today we will talk about SVMs, that is the support vector machines. Okay, so basically, support vector machines, they are used widely for classification tasks. Okay, so we will look only on binary classification using SVMs. Okay, so let's say that let's start with a setup. Let's say I have a data set. Here, your xi belongs to some d-dimensional vector space, and your yi is either -1 or +1. They are labels basically. Okay, so labels corresponding to each and every data point xi. Okay, um, fine. Now we make an assumption. We assume that the data set D is linearly separable. Okay, fine. So I will introduce SVM in two contexts. First, when the data is linearly separable, and then we will see what if the data is not linearly separable, what we can do about SVM. Okay, so let's take the first case. Assume that the D is a linearly separable data set. So what exactly linearly separable means? Linearly separable means that there exists W belongs to same d-dimensional subspace as xi belongs, and B real number, such that W transpose xi plus B is greater than 0 for all I, such that yi equal to 1 and W transpose xi plus B is less than 0 for all I, such that yi equal to -1. Okay, so these are basically hyperplane, right? This is a hyperplane, fine. This is a hyperplane that will separate your data from +1 and -1. There's a hyperplane that separates the data from +1 and -1. So it's saying that a data is said to be linearly separable if you can come up with a W and a B such that if you put your data into that hyperplane, it will classify it as 0 for all the data which actually belong to the class 1. And if you put your data in your hyperplane, it will classify them as -1 for all x's that actually belong to -1. So basically, it's like my data set has some this kind of structure. Fine. So that I can always come up with a hyperplane. Let's say this one is my hyperplane, W transpose x plus B, such that if I take a x from here, I put it in the hyperplane, it will classify that this x belongs to there. If I put a 0 from here, put it in the hyperplane, it will say that my 0 belongs to here. Okay. So basically, it classifies the two portions neatly. Okay. So now the thing is, if data is linearly separable, it simply says that if data is linearly separable, you can always come up with a classifier that classifies both the data, both the data points belong to the different classes, +1 and -1. Fine, such that no misclassification will occur. So for all I such that y equal to +1, for all I such that y equal to -1, it means you can always classify your points such that there won't be any type of misclassification. Okay. Now, in the training set itself, misclassification in the training set. Now, let's say that data is linearly separable. It means that let's visualize. I have this data with me. I have this data with me in R2 plane. Okay. Now you tell me how many such hyperplanes you can draw here. Right. This is a valid hyperplane. This is a valid hyperplane. Basically, these are classifiers. Okay, so let's say this is a classifier C1, this classifier C2, this classifier C3, classifier C4, classifier C5. Here you can make infinite classifiers. Okay. So the thing is, if your data set is linearly separable, then you can always come up with infinite classifiers that separates them. Now the question is, which one of these is the good, or what you say, optimal or best classifier? So basically you ask the question, which one of these is the best or the optimal or good classifier among those infinity classifiers, right? You are left with so many classifiers, but now I'm interested among all the classifiers, which one of the classifier is the best one. Okay, so this question is being answered by something known as SVM that we are going to study, the support vector machine. Okay, so what I believe that, okay, so let's assume that, let's say that, okay, I have this data set again, same thing. And let's say I draw a classifier like this. Fine. And let's say I draw another classifier like this. Okay. So this classifier C1, this classifier C2. Now you intuitively tell me which one of the classifier is good. 2. The reason that I will claim that C2 is better than C1 is because, let's say I give a test point. Okay, so this circled one is my test point. Okay, let's draw it in some other color. Let's draw it like, can't use blue, so I try pink. Okay, so let's say this squared one is my test point. Okay, so for C1, let's assume that I have the classifier C1. So technically, if this particular point lies in this location, then this point should get classified to the class of the blue circles, right? Yes. But think closely that this particular pink point, okay, it lies closer to this axis, this brown axis. Okay, so let's say if I apply a KNN classifier, KNN is neighbor. So in this case, this particular point will belong to this class. So basically, you can intuitively think that this particular pink point is much closer to the crosses as compared to the circles. Okay, fine. So I intuitively, it should belong to the class of crosses because it's their neighbor. But I have a classifier that neatly classifies these two classes, but due to this classifier, this point is getting classified to the classes of circles. Okay. Now the thing is, C2 is a good classifier, fine, because if due to C2, this pink point would get classified to the class of crosses. Okay. Now the thing is, a best classifier, I can define a best classifier as, the thing is, in C2, the closest points on either class are far away from the hyperplane itself. Okay, so if I consider this particular hyperplane, C2, right? If I consider this hyperplane, so you can see the points that are closest to the hyperplane. Okay, this is the particular point that is closest, and this is the point that is closest. It is far away from the hyperplane itself. Rather, in case of this C1, you can see that this is the closest one, and this is the closest one. Fine. So in C2, the points belong to either of the classes. They both are far away. But in C1, the point belonging to the class of the circle is only far away from the classifier C1, but the point that belongs to the crosses, it's close to it. So basically, C2 is giving more room to the test points to get classified correctly. Yes. Right? In case of C1, it's not giving more room to the test points to get classified into the circles, right? see, if you give a test point to the C1, right? If it's very close to the crosses, even at this condition, it will get classified to the circles.
Yes.
Fine. So it's not giving the test point more room or more space to get it classified to its neighboring class.
Crosses. Yeah.
That was the crosses. But here C2, it's giving them the, what you say, more room or more spaces. Okay. So let's do one thing. Let's draw it neatly again. Okay, you'll better understand. Oops. Let's understand it better. So in C2, you can see that this is the margin, this is the blank margin. So C2 is giving them more room to get classified, right? If I put a point over here, it will get classified to this, as it's closer to these circles as compared to the crosses. If I put a point over here, it will get classified to this. But in case of the C1, the room was not enough. Okay, there is not enough room here. Fine.
The room is more on one side and very
yeah,
less.
The room is more on one side. So basically, we can see that a classifier is good if and only if the point belonging to both sides of the data, either class of the data, are far away from the classifier. In C2, these are far away from the classifier, but in C1, only one point from the classifier is far away of the one class, and the other class, it's closer to this. I don't want this configuration. What I want that the points from the either class should be far away from the classifier itself. In the case of C1, the black classifier, it's not happening.
Yeah.
Only point from one class is far away and another is closer to it. Okay, so that's restricting it, the required room that is required to classify the points correctly. Fine. Yeah. So the green classifier, the C2, it's giving me more room. More room to classify data correctly. Classify test data. Correctly. Fine. So how can I write it mathematically? So the thing is, I will write mathematically that a good classifier will have a good classifier will have closest data point of either class far from the classifier itself. Right?
Yes.
Good classifier is that. So you have your closest data points. So in this case, these are the closest data points. Green is the good classifier. So it should be far from the classifier itself. Fine. So this is the definition of a good classifier. Now the thing is, let's do some math. Okay, let's say that we know that in this setting, that I've drawn here. Okay, so you can always come up with a linear classifier that will neatly separate the two classes. Okay, C1, C2 both separate the two classes. The training error will be 0. But in testing case, it may happen that the C1 will not perform well, but C2, the classifier that is in the middle, it will perform well.
Correct.
So let's say that there exists a W such that W transpose. I can always find a W and B such that it will equal to 0 for all I, such that yi equal to 1, and W transpose xi plus B less than 0 for all I, such that yi is equal to negative of 1. Okay. Now I can see this is a strict inequality right over here. Fine. By definition, this is by definition of linearly separable data. It's by definition. I can say that W transpose xi plus B is greater than or equal to epsilon and W transpose xi plus B is in turn less than or equal to epsilon. Okay, for all I such that yi equal to plus 1, for all I such that yi equal to -1, where epsilon is a very small quantity. Okay, it's a very small positive real number, and you can say this, right? Now let's say I divide both sides. I divide the both sides by epsilon itself. So what I will end up getting, okay, I will get this now.
Yes.
Let's say that W transpose E is some W tilde and B by E is some B tilde. Okay.
Yes.
So basically you have scaled the W transpose vector using epsilon. Okay. So these two equations will now resemble as so it means I can say that data set.
Less than.
Oh yeah, it will be less than -1. I can say that from the data set, I can always construct if the data is linearly separable. If the data is linearly separable, then I can always come up with some W tilde and B tilde such that the above condition will satisfy, such that the W transpose xi plus B tilde is greater than or equal to 1 for all yi equal to 1, and W transpose xi plus B tilde is less than or equal to 1 for all yi equal to -1. Okay, it's just I have rephrased this a little bit. Okay. Now the thing is, W tilde and B tilde, they are just dummy variables. It means I can say that I can always come up with, I'm just rephrasing the definition of linearly separable, W and B, such that W transpose xi plus B is greater than or equal to -1 for all I such that yi equal to 1, and W transpose xi plus B is less than or equal to -1 for all I equal to -1. Okay?
Yes.
I will stick to this. I will stick to this definition now. Now let's visualize these two. Okay, so basically here I have got two hyperplanes. This one is the hyperplane and this one is the hyperplane, right? So now let's try to visualize it. How does it look? Okay. So it's basically like so the first equation. Let's focus on the first equation. It says that all the xi's that belong to the class 1, okay, it can be the product, the hyperplane, the particular prediction can be either 1 or it should be greater than 1. Okay. So let's say these all are belong to +1 and they all belong to -1. Okay. So if I can just come up, if I can just draw this particular line, it should be something like this. The green equation will correspond to this line. Okay. And the lower one equation, it will be like this line. Fine. So this particularly is the plane W transpose X plus B equal to 1. And this is the plane W transpose X plus B equal to -1. Okay. So all the orange points, all the X points, if I put these X points into the plane, like into the equation, it can be either +1. So if this particular point lies on the plane, it will give me +1. And if the particular point doesn't lies on the plane, it will give me something quantity greater than +1. Similarly, here, if the blue point lies on this particular plane, it will give me -1. So it satisfies the equation, right? And if the point doesn't lies, it will give me something less than -1. Okay, fine. So basically, what this equation says that there don't exist any data point within this particular street. Okay, so it's basically it looks like a street, right? So you have this hyperplane and you have this hyperplane. So these two equations says that all the points can lie either on this side of the hyperplane W transpose X plus B equal to 1, or on this side of the hyperplane of W transpose X plus B equal to -1. And no data point lies between them. Fine. So these two constraints just says that there don't exist any data point that lies within this particular between the hyperplanes. Okay. So if your data is linearly separable, then it means you can always come up with two hyperplanes, W transpose X plus B equal to 1 and W transpose X plus B equal to -1, such that no data exists between these two hyperplanes. Fine.
Yeah.
So the conclusion is this: if your data is linearly separable, then you can always come up with hyperplanes W transpose X plus B equal to 1 and W transpose X plus B equal to -1, such that no data lies between these two planes. Okay. So just give me a minute. Just a minute. I have to adjust a bit. Okay. Okay, so the thing is, okay, yeah, if your data is linearly separable, then you can always come up with two hyperplanes, this and this, such that no data point lies between these two planes. Okay, now how do I, this is the condition, okay, let's mark this condition as condition number 1. How do I club these two conditions? So I can always write these two conditions, W transpose X plus B equal to +1 for all Yi equal to 1, and W transpose X plus B equal to -1 for all I equal to -1. I can always write these two as, sorry, not +1 -1, it should be greater than equal to +1 and less than equal to -1. I can always write these two as the Yi times of W transpose Xi plus B greater than 1 for all I. Do you agree?
Yes.
See, if I have a Xi that belongs to -1, so Yi will be -1 and this inequality will flip. And if Yi is +1, then this inequality will remain intact. Okay. Okay. Fine. So I can write it as this. Okay. So now what was my task? I have said that a good hyperplane is that such that the closest point to the hyperplane on either of the class, they should be far apart. Okay. This is the what you say notation of a good hyperplane or the characteristic of a good hyperplane. So let's draw a thing and let's formulate this problem neatly for the good hyperplane. Okay. Let's say I have these points. Okay. So again, this line is W transpose X plus B equal to -1. This line will be X plus B equal to +1. Fine. So what I want a hyperplane that is far from these two closest points. Okay. So these two will be the closest point to the hyperplane, any hyperplane that I draw here.
Yeah.
Right. So I want a hyperplane
Exactly.
that exactly lies in the middle such that this point is far apart from it, and parallelly this point is also far apart from it. I don't want a hyperplane such that only one point is far from and another point is close. Okay. that won't give me enough room for the test data set to get correct classification. I want a hyperplane such that it satisfies two conditions, that it satisfies both the data point from the either of the class should be far apart from each other. Okay, I want a hyperplane like this. And to estimate this hyperplane, what I need, I want to find the W, the best W that will give me this particular green hyperplane such that the points from either of the class is far apart. Okay, so it's basically, there are some terminology. This particular thing is known as the street. Okay, so basically it's known as the widest street approach. Fine. So I'm planning to generate a hyperplane such that these two points will be far apart. Okay, now what I will do, so basically what I want the distance between okay, so distance, what I want the distance between what I basically want the distance of my hyperplane that is parameterized by some W, okay, with respect to this particular point star, okay, to be far, plus distance of my hyperplane W with respect to this particular point to be far, right? So it should be, basically it should be max. I want to maximize the distance, right?
Yes.
I have to choose a hyperplane such that the distance between my hyperplane and the closest point in one class is maximum, as well as the distance between my hyperplane and the closest point with the other class is maximum. So I want to satisfy these two. Fine. Yeah. So let's compute the distance between
okay, so that plus is notational.
What plus?
This
This plus, no?
Yeah.
Yeah, I want to maximize these two distance consecutively. Consecutively, like parallelly. So the distance between the W transpose X plus B, that's my hyperplane that here the W I'm estimating. The distance between the W transpose X plus B, and how do I the hyperplane W transpose X plus B and closest point of what I want to do, I want to maximize this. The distance between W transpose plus B. By the way, this particular green point, this hyperplane is basically this W transpose X plus B equal to 0, right?
Yes, central.
Fine, central, yeah. So the distance between W transpose X plus B, the hyperplane that I'm generating, that I'm estimating, and the closest point of this star class plus the distance between W transpose X plus B, again the plane that I'm generating, and closest point of this particular circle class. I want this to be maximized, right? So I have two terms over here. This one is the first term, this one is the second term, okay? So basically you can say that this one is the distance D1, this one is the distance D2, fine? I want to maximize these two. Yes. I don't want my D1 to be get entirely maximized, because in this case D2 will be not maximized, and vice versa. I want these two to be on the same page. Correctly maximized, okay? So basically this particular generation, this particular thing is called the support vector machine. It's called the SVM, okay? So SVM will give me a classifier. It's known as the maximum margin classifier, such that the distance of points from the either class will be high. So this is the classifier that is given by the SVM, okay? So the objective function of SVM is max of D1 plus D2. Okay. Now if you have done some basic +2 level of math, then you can find the distance between a plane and a point, and you will see that the SVM objective will boil down to max of 2 by W2 norm square.
Yes.
Fine. So this is my SVM objective function. I'm supposed to maximize this function, okay? But will it really give me a good hyperplane if I just maximize this function? No, it won't give. The reason being, see, I have these points with me, let's say. Fine. If I just maximize the D1 and D2, if I just maximize the distance D1 and D2, okay, I will end up getting a hyperplane over here, because that the distance between these two is also maximized, right? This will be D1 and D2. Fine.
And that being at infinity.
Yeah, it can be anywhere, right? As far as the distance is greater,
Yeah,
it can be anywhere.
that
So
will lead
if I
to-
solve this optimization problem, I will always end up getting a plane like this.
Yeah.
Fine. So what I do, I want to maximize D1 and D2. So it's basically D1 plus D2. I want to maximize this subject to constraint. What will be my constraint? That no points lie between the hyperplane minus 1. See, I want this particular plane, right? And I want that my D1 and D2, they should be maximized. But I don't want this particular plane to pop up here. Okay, so what I do, I basically want it to be between these two planes, right? Between these two. I want my hyperplane, the SVM hyperplane, between these two vectors, between these two hyperplanes, right?
Because only in that case the points will not be between the.
Yeah, exactly. So I want to maximize my D1 and D2 within this particular range, within this range. Fine. I don't want my green classifier to pop out here.
Correct.
Fine. So the constraint that I will put that, you give me a optimal hyperplane, this particular light green one, okay, so that your D1 and D2 is maximized and no data point should lie in this space within the margin. This is called as the margin. So that no data point will lie within the margin.
Okay.
So in that case, my optimal hyperplane won't pop up here.
Correct.
Okay. If it would pop up here, then yeah, definitely there's this many data points exist between these two hyperplanes. So basically, I want a hyperplane one such that D1 and D2 is maximized and no data point pops between the margin.
Yeah.
Okay. So how do I write no data points pops within the margin that I've written it earlier? Here. Fine. This thing, yeah. So this two equation says that no data points lie within the margin. Fine. So always any of the data point, it can lie either this side or this side of the margin. This two equation says. Okay. So my final SVM optimization objective function will be this. Maximize your this subject to constraint, no point lies between them. And I can write it systematically as, let's say, SVM objective function is max of 2W subject to constraint yi w transpose xi plus b is less than equal to 1. No, sorry, greater than equal to 1. Yeah. For all I, let's say there are n data points of n. So this is my SVM objective function. Or this is the optimization problem that I'm supposed to solve with respect to W to get a maximum margin classifier, that is my SVM. Okay, so up till this, it was only the problem setup. Fine, so this is the optimization problem that I want to solve to get the maximum margin classifier. SVM is known as the maximum margin classifier. Okay, SVM. Fine, so I have the problem P with me. Let's tag this problem P. Now let's solve it. Let's try to solve. It's basically a constraint optimization problem. Fine. You're supposed to optimize a particular function with respect to some constraint. Okay. So for that, we need to introduce you to constraint optimization. Let's say the theory of constraint optimization, how to solve this kind of optimization problem. how to solve optimization problem that has some constraint with it. Okay, so let's try. Let's introduce with some basics theory of constraint optimization. Okay, so theory of constraint optimization. Let's try to introduce you to the theory of it. Okay, fine. So in constraint optimization, let's say you have a function. Let's say minimize with respect to x. Fx is your function, and these are your constraints. Let's say aj transpose x plus bj is less than equal to 0. J belongs to 1 to k. Okay, and let's say aj belongs to Rn dimensional space, bj belongs to real number, and f is a function from Rm to R. Okay, how do you solve such kind of optimization? I have a function, want to minimize, but the solutions should also satisfy this particular constraint. Okay, so how do we do that? So let's define something. A point x belongs to Rm that basically how many constraints do I have here?
K.
Yeah, I have k number of constraints, right? So a point x that satisfies aj transpose x plus bj greater than equal to 0. Sorry, it's less than equal to 0, right?
Yeah,
it's less than equal to 0. For all j. A point x that satisfies all the k constraints. Okay, we tag this point as feasible point. Fine. Now, here we will take a case. We assume that the function f is a convex function. Okay. See, here your function is a convex one, and your constraints are affine constraint. Okay. So they are affine constraint. Okay. So what happens that when you have a okay, by the way, this particular fx is known as the objective function, and these all they are known as the constraints. Okay. Okay. So if your objective function fx is a convex function, and if your constraints are affine constraint, okay, if your constraint are affine constraint, then it can be solved easily actually. Okay, so it has some definite set of rules. It can be solved easily. Okay, so now the thing that I will introduce is this is something known as the Lagrangian. How do you solve this kind of optimization problem? So the first thing, you construct a Lagrangian. Fine. So your Lagrangian will be a function of x and let's say a function of mu. Okay, the Lagrangian will be objective function plus sigma I equal to 1 to k mu I ai transpose x plus bi. This is a Lagrangian. Fine.
yes.
So if you want to optimize this problem, if you want to minimize this function with respect to this constraint, what you do, you simply construct a Lagrangian and minimize the Lagrangian. Fine.
Yes.
It's a minimization problem, right?
Unconstrained.
No, it's a constraint minimization
Second,
problem.
after writing the Lagrangian.
Yeah. So if you have a constraint optimization problem, minimize of x, you can construct a Lagrangian and minimize it. If that problem is maximize fx with constraint, then you can maximize the Lagrangian with
without constraint.
yeah, then you can maximize the Lagrangian, right? So basically, whatever constraint optimization you have, you construct a Lagrangian and do the optimization for the Lagrangian. Okay. Now there is something known as the KKT condition. It's something Karush-Tucker's condition. Okay. So there are something known as the KKT conditions that we will define. Okay. So the condition is that KKT condition for when your function is convex. So we will define KKT conditions only for the case where f is convex. Okay.
In general, this is the case that they are defined only for convex functions?
No, KKT conditions can be defined for any objective function, okay. But yes, okay, fine. Let's define for any arbitrary function. Okay, let's just define the KKT conditions. Okay, KKT condition says that okay, let's define it for convex. Okay, I don't want to get into optimization, so it will be a separate course on optimization. So for the sake of time, let's define KKT condition for f to be convex only. Okay, so what it says that any x star is a global minimizer if x star is feasible. I've already defined what is the feasible point. Okay, if x star is feasible and there exists mu j star such that, or there exists a mu j, there exists a mu star such that, number one, if I take the gradient with respect to Lagrangian and put x star mu star, I have to get 0. Mu j star should be greater than equal to 0 for all j. Okay, so basically I have k number of mu i's with me. Okay, so if I just write a mu, so it's basically a k-dimensional vector.
Correct.
Fine.
Yeah.
And mu j star and aj transpose x star plus bj should be equal to 0 for all j. Okay, so KKT condition says that any x star is a global minimizer if x star is feasible and there exists a mu star such that these three conditions should be satisfied. Okay, so these three are KKT conditions, and these are only for if f is convex 1. Okay, so if f is convex 1, then I can find a tuple x star mu star such that these three conditions can be satisfied. Okay, so for f convex and affine constraints, if I can find a x star and mu star that can satisfy all the three conditions, then I can say that my x star is a global minimizer. Okay? Yeah. This is the definition. For a constraint optimization problem where f is a convex function and constraints are affine, and if I find a point, this is known as the KKT point. If I find a KKT point, x star mu star, such that it satisfies these three conditions, it satisfies the KKT condition, then I can guarantee that x star is a global minimizer. Okay. Only for the case when f is convex. Okay.
And constraints are affine.
Yeah, constraints are affine. Okay. Now you can see that we have this constraint. Aj transpose x plus b is less than equal to 0 for all j, right? Fine. So for a particular x, let's say for x bar, if a constraint ai transpose x bar plus b is equal to 0, the constraint is an inequality 1. If for a particular point x bar, if I get an equality constraint, fine, then for that point x bar, the ith constraint, fine, the ith constraint belong to active set, I can say.
Okay.
So any constraint, let's say an I, the ith constraint, okay. So I have k constraint now. I belongs to active set if ai transpose x bar plus b equal to 0. Okay. The active set is defined for certain points. Okay. They are point dependent.
Okay.
Fine. So for any point, let's say it's a point x bar. Let's say if you find a point x tilde, then it's possible that the ith constraint is not satisfied with the equality. Some other constraint is satisfied with the equality.
Okay, so it is not necessary that there will be x tilde.
The thing is, for this set of constraint, if you came across a point such that this point is making some of the constraint as equality, then I can say that those constraints belong to the set known as active set
For that X tilde.
for that particular
Okay.
X. Okay. This is the concept of your active set. Okay. So active set. Okay. Let's say A is the active set. This is the set of all J such that AJ transpose X tilde plus B is equal to 0. Fine?
Yes.
This is active set. Active set for X tilde, let's say. Denote it like this.
Okay.
Fine. Okay, so now we will define something known as dual. Okay, so what is a dual? Now let me define it. Okay, so the problem, let's say, yeah, let's say I denote a problem P by min x fx, fine, subject to constraint AJ transpose plus BJ is less than equal to 1 for all J belongs to class 1 to K. Okay, let's say it's a P. So I can construct a dual problem for P. Okay, so basically P here is known as the primal problem. Okay, fine. So how do I define a dual? What is a dual? The dual problem of P is basically defined as Q of mu. Okay, and it's equal to the infimum of x Lx mu.
Okay.
Fine. It's basically you are doing an unconstrained minimization of your Lagrangian. You have a problem P. Fine. You compute its Lagrangian. And then you do a unconstrained minimization of your Lagrangian with respect to variable x.
Okay.
So basically Lagrangian is a function of x and mu. Fine.
Yeah.
So if I do an unconstrained optimization of x and find a minimizer x star and I put back the x star over here, okay, I will get a function in terms of mu only. Fine. And that particular function is known as the dual. Okay. See, the thing is, the computing dual is a tricky one. It's not that simple as it is. So basically, my Q is a function of mu, right? So mu belongs to RK dimension, right?
Yeah.
So Q is basically known as the dual function of Q is a dual function. Yes. And we know from the KKT condition, mu should be always greater than or equal to 0. Fine.
Infimum is greatest lower bound, right?
Infimum, yeah.
Supremum is least upper bound.
Yeah, exactly. So this is okay. This is a dual function. Okay, you can construct a dual function. What you do, you compute the primal of your Lagrangian L. Fine. You optimize it over the x. You find the x star. You put back the x star over here, and you get a function in terms of mu only.
Correct.
Fine. So this is a dual. I will tell you how to construct a dual function. Okay, it's just a basic definition, but in constructing a dual function, you will encounter problems. Okay, so I have a primal problem P. Now I define D as the dual problem. My dual problem will be, if I have minimization in primal, in dual it will get maximization. Okay, maximization of u, qu, subject to constraint, mu is greater than or equal to 0. So basically what you do, when you have this kind of Lagrangian, when you have this kind of what do you say, constraints, okay, with inequality when you have inequality constraint, then they are Lagrangian multipliers. So basically the mu i's, they are known as the Lagrangian multiplier. Okay, these Lagrangian multiplier are supposed to be greater than or equal to 0.
Okay.
If your constraint is an inequality constraint, your Lagrangian multiplier will be greater than or equal to 0. But if your constraint is an equality constraint, it can be any real number.
Okay.
Fine. So we are only dealing here with inequality constraint. Hence the mu's, the Lagrangian multipliers, will be greater than or equal to 0. And hence the mu is a Lagrangian multiplier. It should be greater than or equal to 0. Fine.
Yeah.
So this is the dual problem D. Fine. So from a given primal P, you can construct a dual problem D. Okay. So let's define something known as primal dual relationship. Okay. So first thing is, if primal has a solution, it implies the dual have a solution, and optimal values primal and dual will be same. Okay, and it will be same. Listen, this primal dual relationship is only for the objective function of your primal to be convex and affine constraint. Okay.
Yeah.
So basically, in general case, it doesn't happen. In general case, if your primal and dual have a solution, then the optimal solution of your primal will be always greater than or equal to your dual. Okay, in general case.
Okay. General case.
Let's say P star is optimal solution of my primal,
Hmm.
and D star is optimal solution of my dual. Okay.
Okay.
So P star is basically Fx star.
Hmm.
D star is basically Q mu star. Where mu star and X star are both feasible points.
Okay.
Fine. So in theory, it should satisfy like this.
Yeah. Okay.
But here,
when the constraints are,
we are dealing with the primal objective function
convex.
Fx convex,
Constraints are fine.
and fine constraints. So I can say that P star is equal to D star. Okay.
This is what is a strong duality. Right?
Yeah, this is known as a strong duality, by the way. Those who know optimization, they will call as a strong duality, and this particular thing is known as the weak duality. Okay. Fine. Now the second thing is the X star that you have found is optimal for primal, and mu star is optimal for dual. Okay, so if X star is optimal for primal and if mu star is optimal for dual, then yeah, it's optimal for primal and dual, and X star is primal feasible. It means it's feasible in primal problem. Okay, and mu star is dual feasible. So basically, X star is optimal. If X star is a primal point and it is the optimal for primal, and mu star is a optimal point and it's also feasible for the dual, then you can say that what I've written earlier, it's just the writing mathematically the equation number one, Fx star. Fine. So what will be Fx star? It says that Fx star is equal to basically this particular thing, right? Q mu star, okay? Or you can write that Fx star is equal to Lx star mu star, right? It's from the KKT conditions, right? In KKT, what I have said that if your Lagrangian satisfies these three conditions, if there exists X star and mu star that satisfy these three conditions, then your X star is a global minimizer.
Correct.
Okay. So Fx star equal to this. I can write it as this, right? X mu star. Fine.
Yeah.
And this is nothing but your Q mu star.
So Fx star is equal to L of X star, U star. Yeah.
See, this point, okay? Min of X Lx mu star equal to Q mu star, okay?
Yeah.
Because min of X, Lx and mu, it will be Q mu. So for mu star, it will be Q mu star.
Correct.
Okay. So this term you should know is known as a strong duality. So the primal and the dual problem, they hold the small duality. Okay. Fine. So we basically denote them as P star equal to D star. Okay. Okay. Now let's come back to SVM optimization. Okay, enough of optimization theory. Let's come back to SVM problem. So what is the SVM objective? You know of AW, subject to constraint. Subject to constraint. So it was maximize. Fine. Subject to constraint this. Okay.
Correct.
Now let's tweak this particular thing. I can write the maximization as minimization. If I flip this objective.
Correct.
Okay. And I can write the subject to constraint thing as this. Fine.
Yes.
Let's say I have n data points or n number of constraints I have. Okay. So my task is to solve this. So this is a primal problem. Okay. This is a primal. Let's solve this. Okay. Let's solve this using the Lagrangian. So it's your fx. It's a convex function, and your constraint they are affine. Right. If I just compute the Lagrange, if I just write the KKT conditions, and I will get its global minimizer.
Correct.
Fine.
Yeah.
So let's construct the Lagrangian. Okay. Now let's write the KKT condition. Let's find a point W star and mu star. KKT condition says this, right? Next time mu star. Okay. Now, okay. So what will happen if I take its gradient derivative? So it will be W plus the mu I won't matter. Okay. It will get cancelled out. So W plus it will become minus, right?
Minus y, right?
Just n mu I y I xi equal to 0. Okay. So your W star will be so as my objective function is convex and constraint are affine, then the KKT conditions are sufficient for my optimizer. Okay, so it's acting as optimizer. Okay, W star, the optimal W is, so this is the optimal W. Okay,
yes.
This is my optimal mu star. This is my optimal parameter for hyperplane. Okay, right? This optimal parameter for hyperplane. So this is just the first one. Now let's compute the gradient with respect to B also. Okay. So what will be the gradient with respect to B, Lagrangian? I will be left with, okay, summation of mu I by I equal to 0 only, okay? Yeah. Fine. The third KKT condition is that mu I star and 1 minus W star transpose for all I. Okay. And the fourth KKT condition is fine. Okay, now listen to me one thing, okay? There's one thing that I forgot to tell here. The product of my Lagrangian multiplier and my constraints, it can be anything, affine constraint or anything.
Yeah.
The product of my Lagrangian multiplier and constraint will always be 0.
Okay.
Okay.
Complementary slackness.
This is known as complementary slackness. Those who have done optimization, they may know it. So the thing is, for a particular x, okay, there will be some constraints which will be 0. So that's what we define as the active set, right?
Active
set of all j such that the constraint j transpose x plus bj equal to 0. Fine. So let's say if I have k number of constraints, okay, and let's say my active set is some k dash. length of the active set is k dash, okay?
Hmm.
Which is definitely less than k.
Hmm.
So how many constraints that I am left with that doesn't satisfy the equality for this particular x?
Equality will be satisfied by all, right? This product will be 0.
No, this particular equality for a particular x, right?
Okay,
I can
active
constrain
active
an,
constraint you're saying.
for a particular x, I can constrain an active set, right? Active set is a set of all constraints such that a constraint will satisfy equality for this particular x, okay?
Correct.
And let's say that the length of the active set is k dash,
Hmm.
and I have total k constraints.
Hmm.
So how many constraints will be there that doesn't satisfy the equality?
K minus k dash.
K minus k dash don't satisfy the equality, okay?
Hmm.
Now the thing is, for all the constraints which satisfy the equality, this particular thing will be 0.
Correct.
So for all the constraints where the equality will be satisfied, the mu j, it will be strictly greater than 0 for all j belong to active set.
Correct. Yeah.
Fine. And for all and mu j will be equal to 0 for all j not belong to active set.
Yeah.
So your Lagrangian multiplier, fine. So your as it's a your Lagrangian multiplier will become 0 for all the constraint which doesn't belong to the active set, and your Lagrangian multiplier will not be 0 for all the constraint that belong to the active set. So in this way, this particular thing is satisfying. Fine.
Correct.
So if I have some j such that this particular thing is getting satisfied, okay, equality is being satisfied, it will be 0. And mu j will be non-zero. Non-zero and 0 will be 0. And if this is some real number, if it's not equal to 0, for all those constraints which doesn't belong to the active set, I will have my mu j equal to 0 and it will make it 0.
Correct.
Fine.
Yeah. But one question. For those active constraints where there was equality, there also mu j could be 0 because 0 into 0 is also 0.
No, there can be 0. That's the thing. Complementary slackness says that.
Okay. So
Okay. At the end of the day, I have to make the product of Lagrangian and my constraint to be 0. I can do it in two ways. Okay. If I have the active constraints such that it will satisfy the 0 equality,
then
I will put my mu j as non-zero. And for all the non-active constraints, I will put my mu j as equal to 0 and make it 0. Okay. Drive it to 0. So this was the little recap. Fine. So that's why I wrote this particular stuff over here. Okay.
Yeah.
Okay. Fine. So this is the thing. So my optimal. What will be my optimal W star? My optimal W star is
summation
mu I star. No, see the thing. Your mu I star, okay? It won't be non-zero for all the n constraints.
Correct. Yes. As we just saw.
So we will look at this particular condition. Okay. There we have x star as the point. Here we have W star as the point. Okay. So the thing is, let us define a set S is a set of all I such that mu I star is greater than 0.
Yeah.
When mu I star is greater than 0? Strictly greater than 0.
For active constraints.
Exactly, for active constraints. So my constraints here are my constraint here is this, right? So mu I star will be greater than, strictly greater than 0 for all the constraint, which will be this.
Yes.
Fine. So set S contains all the I. Okay, such that, okay, I was dealing with this now. The W star transpose yi, the W star transpose xi plus b star yi equal to 1. Okay, we are dealing with mu I star. Okay, fine. Fine. So mu I star is greater than 0. It means the particular constraints are equal to 0. Okay.
Yeah.
For all I belongs to S, which means this is satisfied for all I belongs to S. I have total n number of data points, okay?
Correct.
And all the xi that satisfy this constraint.
Yes.
How can you visualize these xis? So basically it's saying...
They lie on that those planes.
Exactly. Basically it says that fine. It is true for all I belongs to S. Means that I have this plane W star x plus B equal to 0 is on separating hyperplane, okay?
Yes.
And on let's make this quickly. What it will be? W transpose x plus B equal to -1, and what it will be? W transpose x plus B equal to +1. Fine. So for all I belongs to S, okay? So it is true for all xi. So it means these three. Okay. So all the xi's that satisfy this particular constraint, they are known as the support vectors. Okay. It means the i's that are in the set S that are actually in the active set. Okay. So for each and every I that belongs to the active set, there exists a xi. And for that particular xi, we can see these two equations to be satisfied. Okay. For all the xi that belong to the active set S. Fine. Now if you visualize this, it's like these particular xi, they lie on this particular planes W transpose xi x plus b equal to 1, W transpose x plus b equal to 1 equal to -1. Fine. So these particular points that lie on this particular two planes, they are known as the support vectors. Okay. So let's define a set S dash equal to set of all xi such that I belongs to S. Okay. So all those xi are known as the support vectors. Fine.
Yes.
So earlier, my W star was what? I2 and mu I star yi xi. Now it will be what? For all I only belongs to S. Because my mu I star, it can be 0 or it can be non-zero.
Yes.
Fine. So when mu I star is non-zero for the active constraint, right? Then my I belongs to S.
Correct.
So S is basically an active set, okay?
Yes.
Fine. So active set I can define is all the constraint can be satisfy equality or all the Lagrangian multiplier can be 0. Fine.
Yes.
So this is my optimal W star. So my optimal W star of the SVM can be written as this. Fine. So this is my optimal hyperplane. Now the thing is, I can say that my optimal W star is nothing but linear combination of support vectors, right?
Yes.
This is a point to note. Fine. Now, this is a W star. How do you get the B star? So for all I that belongs to the active set S, I can have this, right? Now you can compute the B star. B star is this.
Yes.
So as you can see that for different I will get different B star, right?
Yes.
Hello?
For different data points, you will get different.
So what you do, you take mean of B star. Okay? The mean of all B stars. Okay? Now if you can observe, so my W star is determined by the mu I star. Right? I have said that my optimal W star is this. I know yi and I know xi. I can find it from the data set. But what about the mu I star? How can I find the mu I star? So to find the mu and star, you have to compute dual of the SVM primal, okay, and solve dual to get mu star. Okay, once we solve the dual to get the mu star, I will put the mu star over here and I will get my optimal higher plane. Okay.
By the way, these xi, yi are support vectors.
Yeah, these are support vector. I belongs to S now. Yeah. Okay. So yes, you compute the dual of your primal and you put it here. You will get the optimal W star. Okay. So yeah. So now we will talk about the dual. So it's just a end of part one. Okay. Let's say this end of part one. In part two, I will talk about the duals and other stuffs known as the kernel machines.